Hello, everyone. My name is Raluca, and I'm a security professor at UC Berkeley. Today, I'm going to tell you about our efforts on a secure collaborative learning platform. The problem we are addressing recurs often in society. There are many cases when organizations wish to learn from the data across different organizations, yet they cannot share data with each other because this data is sensitive. Let me give you one example, but there are many examples. Banks want to detect money laundering. However, criminals hide their traces across different banks. So if a bank looks only at its own transaction data, they won't be able to catch many of these criminals. That's why the banks want to learn from the data across different banks. But the banks cannot share data with each other because they're in competition, so they won't share customer transaction data. And this is a real situation. For example, the chief risk officer of Scotiabank, and we are collaborating with the Scotiabank, says that collaboration will be vital. The ability to put together our data sets and collaborate on topologies of attack through the use of both advanced encryption and analytics methods will enhance yields by orders of magnitude. And here's referring to how much money laundering they can catch. And besides this, there's many other use cases. For example, in the financial sector, one can use financial forensics to detect human trafficking and sex trafficking or fraud. Also in the medical sector, before the pandemic, we were talking to Kaiser about using collaborative learning for flu prediction models. So that's quite an irony. And this is also useful for nuclear facility auditing when there's sensitive data involved, or cloud-based video analytics for homes or census and whatnot. This is why my students and I have been building the MC² platform for secure collaborative learning. MC² stands for multi-party collaboration and competition, and it embodies the principle of sharing without showing the data. MC² is an open source effort that I'm leading in the RISE lab. At the high level in MC², what we're building is efficient, secure collaborative computation for everyone. And for everyone, what I mean is that there's all these many use cases that I mentioned that could benefit from secure collaborative learning, but the people who would like to deploy this kind of use cases could be data scientists or systems people, but not necessarily security or cryptography experts. So we would like to empower them with a platform that is easy to use, even without security expertise. So in MC², we expose a Python DSL that anyone can use to write their computing task in it with no expertise of security or cryptography. Now, our Python DSL also captures policies. And what I mean by policies are things such as, when can we release a model? Maybe only when it's good enough, when it helps every single party, not just one party. Or privacy policies such as, how much data does the model contain about my data? How much is it leaking? And things like this. So it's possible using MC² to set up an end-to-end policy on data privacy, on auditing, accountability, and things like this. Now, to actually enable the secure computation over sensitive data and to enable it in an efficient way, we are using two technologies in MC². These are two different technologies that have a trade-off between them, and one is better than the other depending on the use case at hand. So one is secure multi-party computation, or MPC, and the other is hardware enclaves. So let me tell you a little bit at a high level about each one of them. So MPC is entirely based on cryptography, so it's a software-based solution. In MPC, you have N parties that have sensitive data they are not willing to share with each other, but they want to train or learn a function F or run a function F over all their data and learn the result of the function F. They jointly want to know that result, but in the process, they don't want to share their data with each other. So no party should learn anything about the data of each other, of another party, other than the function result. And this is exactly what MPC enables. Essentially, what happens is that the parties encrypt their data, they share it encrypted, so the other parties can't decrypt it, they can't see what it is. But then parties compute on each other's data in encrypted form without decrypting it through the power of cryptography. And then they obtain a computation result that's encrypted and they jointly decrypt it. So throughout this whole process, the parties exchanged only encrypted data that they cannot decrypt, and they learned only the final function result and nothing else about each other parties' data. Now, the other approach to secure computation is via specialized hardware, such as hardware enclaves. Hardware enclaves, for example, Intel SGX, Keystone, MI6, Nitro enclaves, they offer a hardware-enforced isolated execution environment that protects even against an attacker that has root access on a machine. The way they work is that essentially on the die, on the processor, there's this memory encryption engine, ME, that encrypts all the data that goes out of the die into main memory and decrypts data coming in. So on the memory, you only have encrypted data. So even if an attacker has root access to the machine, they can only see an encrypted memory. Now, these two approaches are separate and they have a trade-off. MPC tends to be slow and expensive for complex computation or big data. And it also requires a cluster computation at each organization. On the other hand, hardware enclaves don't have these downsides, but they require trusted hardware, which brings trust assumptions on the hardware vendor, as well as a specialized setup. But now when it comes to the setup, we have clouds such as Azure Confidential Computing that offer hardware enclaves, or right now, even Google and Amazon are about to offer clouds with enclaves. But enclaves suffer from side channel attacks, and the cryptographic solution of MPC doesn't have. So there's a trade-off between the two of them, and the right one to use depends a lot on the use case. And we've worked with a number of industry collaborators, and we've seen that each one of the approaches is better than the other in different use cases. My students and I in MC Squared, we have contributed to both of these directions, and we provide systems that can do collaborative learning in both of these, using both of these technologies. Our contributions are aimed at reducing the downsides of these two technologies while keeping their benefits. So for example, in the case of MPC, we have developed efficient protocols that can do CNN inference in the case of Delphi, linear models training in the case of Helen, general analytics or ML in the case of Senet, or classical ML inference in the case of Bost et al. For hardware enclaves, we have targeted side channels, namely protecting a large class of side channels by designing oblivious algorithms. For example, Visor is for ML inference, OCQ for distributed analytics, Oblix for multi-user search, Opaque for analytics, and we also have work for general programs such as Civet and Membuster. So we have put together our projects into creating our MC Squared platform, which is open source. At the moment, MC Squared is not on Ray, but there's an effort in our group for porting a part of these projects on Ray so that one can also do collaborative training in a secure way on Ray. MC Squared already has some adoption. For example, IBM has used Opaque, which is a part of MC Squared for 2 medical use cases, Ericsson for a telecom use case, and Financial and Alibaba for financial-oriented use cases. And Microsoft and Scotiabank are in a partnership with us for the anti-money laundering use case that I mentioned at the beginning of the presentation. And this is really just the beginning of MC Squared because there's so many other possible places where MC Squared could enable secure collaborative learning. So to conclude, our goal with MC Squared is to enable efficient, secure, collaborative computation for everyone. Thank you.